Hello and welcome to the 109th IUVSTA workshop, the APPEC Technology Forum Vacuum and Cryogenics, where industry meets academia. We want to give you a little teaser by some of our invited plenary speakers about their topics.
I'm Johan Schaffner from DESY and working for axion detectors which we want or will operate here at DESY. And my talk is named Vacuum and Cryogenic Technologies in Large Axion Detectors. Here's a short overview. I just want to go briefly through it. My talk will introduce you with a little bit physics, not too much because we have a technical workshop here. And then I will go further on with IUVSTA experiments, the setup for the YAXO, baby YAXO experiment, and later on the MADMAX experiment. And at the end, I will give a brief summary on all of this. What we are doing here at DESY is more or less we try to cover three kinds of axiom experiments. The first one is the light shining through the wall experiment. This is a laboratory experiment where you try to shoot with a laser on a wall and try to find some light after the wall, because meanwhile the axiom light converts into axiom and back to light again in a magnetic field. So this experiment we make here, and we are already operating here at the DESY, is IUVSTA experiment. Second, we plan to install a helioscope. This is the YAXO, baby YAXO experiment here at DESY, where we try to find some axioms coming from the sun. Also, light is converted into X-ray, and this X-ray we try to focus somewhere in a detector, and therefore we try to detect it. And the last one is an haloscope experiment called MADMAX. This is experiment where we're looking for axion or try to detect axion in our environment, and this would also be an evidence for an axiom that the axiom is dark matter in this case. All of these experiments require cryogenic and vacuum techniques, and I will just give a brief summary here, what I try to cover in my talk in the APPEC meeting end of November.
Hello again to everyone. I'm Bianca Bottino, and I work on the dark side experiment for dark matter direct search at LNGS, so at the Gran Sasso National Laboratories. And I will give you a brief overview of what I'm gonna cover in my talk. So I will discuss a little bit the scientific goal of the dark side program, and then I will enter into more details about the dark side detector, and in particular, I will focus, of course, on the cryogenic system. So the DarkSide 20K project, it's a huge program that it's based in Italy at the underground laboratory of Gran Sasso, and in particular is under construction at the moment in Hall C. The DarkSide detector has a nested structure. So the innermost part is a time projection chamber, so what we call for short a TPC, that will be made of ultra pure acrylic, and this will be basically the target for the dark matter interaction, and it will be filled with liquid argon. Actually, it will be a dual phase TPC, so it will be mainly liquid argon with a small layer of gas argon at the top. And the TPC will be viewed, so the active volume will be viewed by two layers of cryogenic silicon PMs, so photosensors that will be basically at the top and at the bottom of the volume. And on the other side, we will also have a deeper look into the so-called proximity cryogenics, which will serve to basically liquefy and purify all the 700 tons that will fill the huge membrane cryostat. So this is basically what I'm gonna talk about, and thank you for your attention.
My presentation is focused on the activity that we are carrying on in the context of the design of the Einstein telescope detector. Einstein telescope is a detector that should go from the present sensitivities of the second generation of detectors like Virgo and Cagra to the third generation with an improvement of sensitivity of the order of factor 10 in amplitude. Here we will focus on the vacuum of the detector. We are having a configuration, the 15 kilometers L, 2 L, so 15 kilometers, and the triangle of 10 kilometers. So in practice, if we focus on the vacuum, on the aspects of vacuum, we have two main challenges. One challenge is related to the beam pipes. We are speaking about beam pipes of 1 meter of diameters with tens and tens of kilometers, order of magnitude 100 kilometers of beam pipes. And the second aspect concerns the vacuum chambers. We have more than 100 vacuum chambers to be built and installed with different requirements concerning the final vacuum. This facility should have a lifetime of the order of 50 years and should be conceived in such a way to have enough flexibility to host upgrades during, in practice, half of a cycle. So that's all. It's clear that we are in a phase of design study. We are in the phase of developing R&D activities. So the crucial is the involvement of the industry in this step of the project. That's all.
Welcome. My name is Henk-Jan Bulten. I will be presenting the vacuum and cryogenics aspects for ET Pathfinder. That is a facility to research technology for future gravitational wave interferometers. So Einstein telescope is a next generation gravitational wave observatory for this high sensitivity, especially at low frequencies. And that means that for Einstein telescope to be developed, we need to develop the technology. Vacuum requirements are very stringent. For Einstein telescope, it is necessary to have zero hydrocarbon outgassing. The limit is 10-14 hectopascal for light masses and 10-15 hectopascal at the mirror for heavy gases. And the aim is to have less than a nanometer of ice built up in, let's say, 5 years of continuous operation. So these are extreme requirements. So in order to develop that technology, there is a lot of activity worldwide. And in Maastricht, we have a facility that can test these cryogenic technologies and vacuum technologies that are needed. In the ET Pathfinder facility can operate 2 cryogenic interferometers, 1 in each arm, and that with silicon mirrors of the same material as foreseen for Einstein telescope.
So hello, and thank you for having me here. My name is Thomas Tümmler from the Institute for Astro-Particle Physics of KIT. My field of research is neutrino physics and especially neutrino mass determinations from the tritium beta decay. I'm here today to introduce you to the upcoming challenges in our present experiment, the Catherine experiment, and what is coming next in Project 8, QTNM, and finally in Ptolemy, the Catherine experiment. Well, this is the experiment we have here at KIT. This is the world-leading neutrino mass experiment based on single beta decay. We have a strong molecular tritium source, a 70-meter-long beamline, and maybe the largest ultra-high vacuum chamber you can think of, a 1200 cubic meter large main spectrometer. It took us about 15 years to develop all the technologies and the diagnostics and operational parameters to run this experiment. And since now 6 years, we are taking data, but we have to think of what is coming next. So the detector system is currently only counting electrons, and we rely on the filter performance of the main spectrometer. This is the McE filter principle. But for future applications, we want to have a detector system which is able to resolve the beta spectrum much, much finer. And therefore, we want to try to apply microcalorimeters. And therefore, we have to operate them in a magnetic field, and we have to couple a cryo platform at the millikelvin level to a room temperature spectrometer. Here, the next two proposals come into the game, which is Project 8 and QTNM. Project 8 pioneered a method that is not relying on detecting electrons with a semiconductor detector. Project 8 uses the cyclotron radiation that is being emitted from the electrons when they are traveling in a magnetic field. This is pioneered by Project 8, and QTNM is applying these principles. The approach of QTNM, which is the quantum initiative in the UK, is to inject these atoms into a small storage ring and then apply quantum sensors to determine or to catch the cyclotron radiation which is emitted of the electrons in the trap. So here's a lot of vacuum and cryogenics and magnet development involved. On the horizon is the Ptolemy experiment. This is not so much aiming to measure the neutrino mass, but they are trying to directly detect neutrinos that are the remnants of the Big Bang. So this really goes by orders of magnitude beyond that what Catherine Project 8 and QTNM can do. And yeah, I would like to invite you to my talk at the Tech Forum, and thank you for your attention.
My name is Keith Middleman. I'm from ASTEC at STFC Daresbury Laboratory in the UK, and I'm going to talk to you about vacuum developments at Daresbury Laboratory for modern accelerators. Our group has got quite a unique position in that we have our own in-house accelerator called Clara, but we do a lot of conventional research in many aspects of vacuum technology. We look at new research and developments on various new technologies that could be implemented for accelerators. And also we deliver large-scale infrastructure to international collaborators as well for some of their accelerators around the world. So we've got a unique set of skills in terms of vacuum, material surface science, etc. And that kind of puts us in a nice position. We deliver a lot of international projects. So I'll just tell you a couple of those. So we've done a lot of work for the European Spallation Source, designing all of their Linac warm units. We're also working, and we have finished now all of the deliveries for the superconducting, high beta superconducting modules, cryo modules for the European Spallation Source. We completed that earlier this year. We're doing some work with CERN on the high Lumi crab cavity, which is another SRF type cavity to increase the number of collisions for the high luminosity upgrade. We've already built a prototype shown on some of these images here that's been shipped over successfully to CERN, and we're now in the process of building the next 4 crab cavities as we speak. So as well as the work that we do for international partners, we've got a lot of work on research and technology for future accelerators. One of the primary areas that we've been working on for many years is neg coating. We've got lots of different areas that we've been looking at for this particular neg coating and its properties. Each of the bullet points listed here, we've got obviously a lot of detail that I would show at the actual meeting itself in more detail. And then finally, one of the other things that we're doing is some work on superconducting RF thin film research. And we're currently in the process of depositing a single cell cavity. And that single cell cavity will be tested by the spring of next year. So this is part of a wider European collaborative work that we've been doing as well. So that's everything I have. So obviously, thank you for listening.
Thank you for listening to the short introduction to topics of our 109th IUVSTA workshop. And we hope we can welcome you in Maastricht at the meeting on November 24 to 26.